The first talk will be given by Michal Branicki from University of New York.
Actually, it's Edinburgh now, but I've moved. It's Edinburgh now, but it's
Edinburgh. Okay, so University of Edinburgh, and he will talk about an information theoretic approach to improving predictability in partially observed complex dynamical systems.
okay. First of all, thank you. I'd like to thank the organizers for inviting me to give the talk here. So as you can see, the title slightly changed, but the content remains pretty much the same. So I wanted to report on some recent results concerned with a framework for improving imperfect statistical predictions of complex dynamical systems. By complex, I roughly mean high-dimensional nonlinear systems with high-dimensional attractors and lots of multi-scale interactions. And by partially observed, again, I roughly mean that one only has access to a certain small subset of processes involved in the dynamics that is at play, usually the large-scale processes. This is a joint work with Andy Maida when I was still at NYU. So my goal the whole goal of this research is actually quite easy to state. It's more difficult to do other things with it. So on this cartoon, I can pretty much summarize it. So let's just take a snapshot of some complex spatially extended system. Doesn't matter what it is. So at constant time, I'd like to be able to perform statistically accurate predictions of this true dynamics using a coarse-grained model. Okay, so I don't even want to be able to accurately predict the whole trajectory of the system. I want to be able to carry out statistically accurate predictions. Okay, so for example, at this point, I would like to, if the red one is my true PDF, I would like to be able to have a simplified reduced order model that statistically represents at each given time the true dynamics at least the subset of variables that or modes that I can observe. Well, even in this cartoon here, I'm probably the truth that the model is not exactly going to represent it. That would be too much to hope for. I'm very likely to miss a lot of unresolved intermittency, but I would still like to be able to have statistically accurate predictions. What happens in reality is something that again looks much more like this. So the predictions of my cross-grained model are likely to become completely different than the truth. And this is, again, due to the fact that if I do reduced order predictions, I'm neglecting or misrepresenting lots of these under-resolved processes, which actually do play an important role even in the dynamics of the large-scale processes. So there's a number of things that one can consider in this case. I mean, the situation in the reduced order imperfect prediction would be something like this, where my statistics is completely off the truth. So I would like to be able to somehow maximize the information content in the imperfect models and then push it towards the truth dynamics. Again, there's at least two different issues that one can think about. One is sort of going down the alley of multi-scale modeling, perhaps using some stochastic parameterizations in order to improve the reduced order modeling. What I'm actually going to talk about today is something sort of tangent to the issue of reduced order modeling, and it has to do with multi-model prediction. So instead of trying to improve a single imperfect model, because we're kind of going to go to the other part of the spectrum and assume that I have a number of imperfect models, and I cannot modify them, but what can I do with this mixture of the models in order to improve the predictions? Can I do it? So again, the cartoon picture is sort of, I'm sketching it here. Let's say the truth is the density of my, the red is the density of my truth. And I have a number of models, imperfect models evolving. And the question is now, what should I do? I mean, should I use one single model? Should I use a mixture of them? Can I find a condition that I could use in order to decide what kind of mixture of these models I should use, or should I use maybe one of them? So this is actually a frequently and commonly used approach in atmospheric sciences. I'm just showing two different plots here. One is just showing the hurricane tracks obtained from different numerical models. The other one is just showing a constant isobar, a line of constant pressure in the atmosphere. And these are just means obtained from different models. What is commonly done is that people take a bunch of different imperfect models and just take the average of all of them with equal weights. Okay? And this is completely ad hoc, and it's shown to work in a number of different cases. In some cases, it doesn't work. The thing is that I haven't seen so far anything more rigorous that would give any insight as to when one should use one approach or model, one model versus maybe multiple models.
There's been lots of experimentation on this.
Yes.
It's a very big international.
Yeah, of course, yes. I mean, but I mean, there is a lot of experimentation, and this is an important experimentation. I'm not going to give you a silver bullet that will replace all this experimentation. That's not my goal. I'm just I want to have a go at it from a slightly different angle.
Yeah, I can obviously argue that everybody's atmospheric model is really the same one with a slightly different tweaks. So
not always, right? I mean, there's number of different, at least for say in the US, there's a number of different labs that have lots of negative.
There are also negative results that say this is not a good idea.
Yeah. And the question is, well, I'll show simple examples showing when it is a good idea, when it's not a good idea. So I'll just quickly. So the content of my talk is just these 3 points. I'll just go quickly through the very basic fundamentals of this information theoretic framework. I'll focus mainly on the second part, which will have to do with obtaining a sufficient condition for utility of this multimodal ensemble prediction. And I'll finish by just using a simple Gaussian example, which is non-trivial and show a number of different interesting cases, which will illustrate what I'm going to talk about. So again, on this two slides, I'm going to show, first of all, what I'm going to use in order to measure the lack of information between two probability densities. On the second slide, I will show why this measure is useful for what I want to do. So in order to measure lack of information, let's say, so this is the marginal density of the truth on the resolved variables. This is some model. In order to measure lack of information between these two marginal densities, I'm going to use something called the relative entropy, which is well-known functional from information theory. Again, just to give you some intuition, both these cases correspond to significant lack of information in the green density relative to the red. So both the mean variance and higher order moments matter simultaneously, not individually. The relative entropy is not a proper metric, but it retains a number of important metric-like properties. First of all, it's non-negative and zero only when the truth and the model are identical. It's invariant under general nonlinear changes of variables, and it also bounds from above certain metrics like the Hellinger distance, for example. It's also convex. There's a number of convexity properties for this. In particular, it's convex in the second argument, which I will need very, very soon. Again, it's easy to decide to say what I'm going to consider my best model. Okay, so if I have a class of imperfect models, I'll just say that my best model at a given time, say, is the one that minimizes the relative entropy. Okay. Now, the relative entropy has an important property, which is sort of triangle-like equality. In order to show this, I need something called a least bias density. So it's a density which is an approximation of the truth based on L moments. So, for example, the truth is a sort of very non-Gaussian density. The pi2 with 2 moment constraints is just going to be a Gaussian given by the dashed line. If I use the least bias densities, my relative entropy splits into these two parts. And that's actually quite important for the reason.
Just a detail on L moments. The first L moment.
Yes. Oh, yeah. That's sorry. That's just a
PowerPoint. Yeah.
It's just it's just a typo. Yeah. L moments.
But just to make sure, we are talking about probability distributions that are really on trajectories in some very high-dimensional phase space.
So I'm talking about. Imagine, for example, looking at Fourier modes or some modes of your dynamics. Okay. So I'm looking at sort of joint probability distributions of certain, first,
But someone
And-
relates to a dynamics, it's not a static.
no, it relates to dynamics. So I deliberately skip the dependence on T here in order not to complicate the
One should
situation.
have in mind a particular time scale and probably also a particular
No, I'm talking about a number of Fourier modes, for example, or a number of modes. And I'm going to be looking at how it evolves with time.
But then you have already in mind a particular type of models if you speak about Fourier modes.
Some type of mod, yes, but I'm not restricting this to any particular type of models. Yeah, I'm just assuming I have a certain family of models over which I can minimize this. So the important property is this one, for the reason that that I don't know. I assume I don't even know the marginal probability of the truth pi. What I can hope to be able to know is this least bias density. I can say measure the mean and covariance of the truth. So the first part I can't really do anything with. The second part I can try to minimize. Okay, the first part is going to correspond to what I call an intrinsic information barrier in this problem. Okay, I can't do anything using modeling. I can't touch the first part. I can do something with the second part. But it will show in a second. I'll show that this is actually quite useful when I look at multi-model predictions, because this first part will actually cancel out. I'll probably skip this just to go quickly to the directly to the multi-model predictions. So as I was saying, again, I have the issue. So this is at a fixed time. I have two different possibilities. I have a single model, single imperfect model, or I have a whole mixture of imperfect models. I assume I cannot do anything with any of the models. What I can play with is play with the mixture. Okay. Again, I can look at the lack of information between the single model and the truth, or the mixture and the truth using relative entropy. I'm just showing the time, how this model error in terms of relative entropy in particular can vary with time. So this particular picture shows that it corresponds to the situation where model, predicting with a single imperfect model has a pretty large model error. These ones are small. I'll go to the details in a second. It's just to illustrate how I'm going to measure the model error. So now if I want to figure out if it's better to use a single model, this M diamond here, or maybe this whole mixture, I can use the following quantity. I look at the following quantity. So this is the relative entropy of the mixture. This is the relative entropy of the single model. Okay. So if this quantity is positive, okay, it means that my mixture predictions will actually have a larger lack of information than the single model predictions. So what I want for this, I want this to be negative. Okay, this means that my mixture model predictions are actually beneficial. And I will go to the condition in a second. First of all, let me just show you examples based on very simple models that this multi-model ensemble prediction is not always the best idea, especially if you equally weight all the models that you have at hand. So I'm just showing two different scenarios. I'm not going into details into what they really correspond to. But in the first case, you have a situation when using a single model is really pretty bad in terms of the predictive skill. It's a really large, has a really large model error. These blue and magenta curves correspond to two different types of multi-model ensembles. The blue one has just all equal weights, and the magenta one is the optimal one. Okay. In the other situation, I have a completely different scenario. So again, the single green curve is the single model prediction, and the blue and magenta are the multi-model ensemble predictions. You can see that in particular, using multi-model ensemble with all equal weights has a pretty large error and actually is doing worse than you're doing this with a single model. Okay. Strictly speaking, it's not very surprising if you think about it a little bit. And it's even less surprising if you look at it, again, in a bit more detail. So I'm just showing here, I'm not going to go into details of this, but I'm showing a condition which is a sufficient condition for improving imperfect predictions using a multi-model ensemble. So this one is simply, it's formulated here. So the relative entropy between the truth and the single model has to be larger than this convex combination of relative entropies of all the imperfect models. This can be simply obtained just by using the convexity properties of the relative entropy in the second argument and this sort of triangle-like equality that I'm showing down here. And it turns out that that this first part pops up on both types of the inequality and actually cancel out. So I can formulate this condition only based on the least bias densities, which I can actually get a hold on. There's two different types of situations here. Again, I'm just sketching the simplest configuration. So I consider the green model again to be the single imperfect model. The black one is the truth here. If my imperfect model was here, then I would have no lack of information on this marginal on the subspace of the resolved variables. So if I'm here, the question is now, should I, and the models I have at my disposal are these colored dots here. So if I, for example, combine the predictions of the green model with the red model, you can easily see using this sketch that actually I can drastically reduce the model error and improve the predictions of my I can improve the predictions by combining these two models. On the other hand, if I ended up combining these two guys or anything on this side, I will end up with a deteriorated prediction skill rather than improving it. There's also other types of situations where if all my models lie to the left here, I can still perhaps reduce the prediction skill relative to the green model, but I cannot beat the best single model that I have at my disposal. Here, the blue guy remains the same, but here note that if I have a model that lies on the other side of this parabola, convex function, I can actually beat the single best imperfect model using two models which are worse than the single one. In this case, I cannot do it. I'm deliberately not showing here what is in the horizontal line because this is actually problem dependent. And I will show this in the example that I'm getting to in a second. This I will glance over. This is mainly to show that there is one can beat this condition kind of to death, and derive lots of more rigorous statements about this. This little theorem is concerned with rewriting everything in terms of these least bias densities. One thing that I want to point out here that if you present it in this way, especially the last term here, I have linear dependence on the moments of the truth here. This is attractive from the point of view of assessing the force response of complex systems to external perturbations, because I can attempt to use this linear response theory in order to assess what the changes of those moments would be. And therefore, I could even try to figure out what the best mixture of models, given that the models I have, what the best weights in the mixture of models would be for maximizing the predictive skill of the force response of my system based only on the correlations on the present attractor. This sort of comes from the combining linear response theory with fluctuation dissipation type arguments, which I'm not going to talk about today. Let me maybe move to the example, which will take several slides and hopefully will clarify a number of issues that I was discussing. So I'm taking a very simple model. So it's a two-dimensional model here with stochastic forcing. So you can consider to be the resolved dynamics, in this case just one particular mode. And V you can consider to be sort of all the unresolved modes, which are in this particular case, they are linearly coupled to my resolved dynamics. This is sort of toy model which still have some value, at least in illustrating these problems. So as I say, this is all Gaussian. I can determine the conditions under which this system has a Gaussian stable equilibrium, which are defined here. And now the trick will be, okay, so this is going to be my perfect model. The imperfect model is just going to be a one-dimensional Gaussian model. I'm just going to model the resolved dynamics here. Okay? And I want to repeat the situation. So first of all, I want to first tune the attractor statistics of the perfect and imperfect dynamics, and then see what happens if I perturb the attractor and how well the imperfect model is doing. So the first case is in the single model situation. Then I'll move on to the multi-model ensemble. So in the imperfect model, I have three free parameters: this damping, the forcing, and the noise amplitude. Okay. The true dynamics was Gaussian, so I have two constraints at equilibrium. I have to tune the mean and the variance in this case. Okay. So I have two conditions on the mean and variance. I have three parameters. So it turns out that I will still have one free parameter. So I will have a whole one-dimensional family of imperfect models of this type, which will all have perfect, which will be consistent at the unperturbed equilibrium. Okay. Now I can consider the response, the infinite time response to the change in the forcing in the truth dynamics, and it's just written here. It's easy to obtain. Okay, there is these two different expressions. The delta f here corresponds to the sort of small perturbation in the forcing. Well, now if I look at the model error in the predictions of the infinite time response using this imperfect model, I can easily get to this type of formula, where now you can see the following, that there is two different situations, and they all actually are dependent on this parameter A here, which is hidden in this unresolved dynamics. And it turns out that depending on what the value of this parameter A here is, I will end up with drastically different situations in terms of whether I can get good predictions or not. So let's take first A being positive. So this means that this whole first term here is positive. The positiveness of this term here was dictated by the existence of the Gaussian attractor. So in this first case, I have, I cannot, no matter what what value of the free parameter gamma I take, I cannot reduce the error to zero, right? For any finite gamma, this is always positive, so I have sort of intrinsic information barrier to improving the sensitivity. On the other hand, if I take alpha A, this guy here, if it's negative, if it happens to be negative, I can find one particular damping in my imperfect model, for which I will obtain perfect response, infinite time response. Okay. So that's the situation. It just shows how much can depend when one looks at infinite time response, even in relatively simple systems. Although I have this stochastic forcing which mimics all the unresolved degrees of freedom, it shows you how much can depend on what actually happens in the unresolved dynamics. Now, if I consider this problem just by taking a whole mixture of those simple linear Gaussian models, the condition for improving the predictions transforms into something like this. I just have a sort of difference of the two quadratics. And I end up again with two different situations here. So again, I will classify it in terms of the existence of information barrier or the lack of the existence. Let's first consider a situation when there is no information barrier. So I can find a model which will give me a perfect for infinite time response. So then again, it turns out that I can find a whole range of dampings in my imperfect model, which I can use to sort of lying roughly between here and here, which I can use to improve the predictions of my force response. Of course, if the model that I started with, if my single model is already the one with the perfect damping, I'm in a situation like here, and of course adding any other imperfect model will not help me at all in improving my force predictions. The other situation is when I actually do have an information barrier in the problem. And then it turns out that the picture qualitatively corresponds to something like this. Okay, so it turns out that for this configuration, it's impossible for me to find models that would lie sort of on the other side. So no matter what I do, no matter what kind of combination of imperfect models I take, I can still improve the prediction skill, for example, relative to the green model, if I take anything to the right of here. But I cannot reduce the information barrier, which is a sort of which is the lack of information between the best imperfect model and the truth here. I'm just showing sort of two different examples here which back up the idea here. So again, this is the green curve corresponds to the single model here. The blue and magenta correspond to different multi-model ensembles. You can see here that, here I can improve my predictions using multi-model ensembles. Here I cannot improve these predictions. The information barrier again sort of corresponds to this optimal weight multi-model ensemble, and it just picks up the single model, which is kind of the closest to the perfect model. So it actually picks up in this picture, it picks up the one that's the closest to the truth. How am I doing with time? Maybe, okay. I still got 5 minutes, right? Actually, maybe. Yeah, okay. Maybe what I'll do, I'll just I'll get to the summary and maybe wait for some questions here. So I went rather quickly over this issue, so let me repeat the things. So I tried to outline this information, a framework, sort of drawing heavily from information theoretic ideas for quantifying uncertainty and improving imperfect models. Improving imperfect models on sort of reduced subspecies. So this framework is naturally suited to deal with modular and partial observability. This partial observability is kind of corresponding to looking at marginal densities in this problem. Thing that I sort of tend to stress to other audiences, that this information theoretic optimization, when you're trying to optimize, for example, the fidelity at the attractor of the model, requires simultaneous tuning of all the statistical models that you're looking at, not individually sort of tuning mean, variance, and so on. The sufficient condition for improving the imperfect predictions is actually quite easy to obtain. I did not go into details of various aspects of this. I'll give you some references at the end. The multi-model ensemble prediction is not always superior to the single model predictions, but using this particular condition, for example, one could try to figure out, looking, for example, only at the unperturbed attractor statistics and implementing the linear response theory, one could try to figure out when a given multi-model ensemble is useful for making improved predictions. And one thing that, but this can be also extended to, multi-model prediction incorporating filtering and data assimilation, which is something I'm working on at the moment. But I obviously did not have time to discuss. And there's a few references that deal with what I was talking about, especially the last paper here. Well, the two top ones are the most relevant for this particular talk. Thank you. If there's any questions.
Plenty of time for discussion.
Well, first a question for clarification. You didn't mention too much about the dimension of the ensemble. This was in practice we have finite ensembles. So,
well, actually, I was even in this little. I didn't show many of those pictures here. Let me just go. There was one. It actually doesn't depend on the. So even in those simple numerical tests, I didn't have too many ensembles. So what I was looking at, one assumption I do make is I assume having good approximations of the densities corresponding to each individual model. But my mixture density, this is just a finite collection of models. Right? So I have finiteness in terms of the members of the mixture. What I do assume is that I have a good representation or good approximation on the densities corresponding to each individual model. But this is, again, much more realistic than, I wouldn't dream of, being able to run 100 different models. Right.
There's two strategies in numerical manipulation center for ensemble prediction system. One is to have the best model and perturb the physics a little bit. So, and you build that sort of multi-model with the same model. And you have taking a lot of different model developed by different people. Some are rubbish, some are good, and you put that all together.
Yeah.
At one point you said you need to have a criteria telling you which one we should keep and the one we should keep,
Yeah, so
put aside.
it all boils down to it's kind of it's all hidden in this condition. Okay, so these weights here are actually related to the weights in the mixture corresponding to your multimodal ensemble.
But this you cannot test.
Well, you can't test them on the present if you have a sufficiently long time series at your present equilibrium on your attractor. You can test them at equilibrium.
But that's the main difficulty. Do you have enough statistics to?
Well, yeah. I'm not claiming to, but this is at least more realistic. I wouldn't say that you can do some if you really have some time dependent evolution of your truth, then I would say this is not really practical. If you're just looking at the equilibrium, you can hope to gather enough information.
Okay, so the construction of the multimodal ensemble somehow as the intrinsic problem that you mix up different dynamics. So to
Yes.
me, I would say that you have a successful mix if you optimize over a certain time horizon for a certain set of observables, and this thing works well for another time horizon for another set of a different set of observables, because if I optimize with respect to energy at time t, of course it will work good.
You see that what I'm using for optimization is not energy,
No, I'm just saying.
because I would be optimizing just with respect to the variance, for example, right? Of your observables.
No, I'm saying if you optimize with respect to certain criteria, and so you say I have an optimal, a good ensemble, in order to test if it is good, you should test how good this is against criteria over which you have not optimized, because then this means that you are somehow getting the right dynamics. Okay, so if I optimize with respect to the hydrological cycle, I want to see the temperature rise. Otherwise, if I optimize with respect to the hydrological cycle and I test the hydrological cycle, it will sort of work by construction. So the question is, I don't see how you end for different times. Otherwise, I don't have the dynamics. I'm just thinking. So I'm not seeing the path. It seems to me a little artificial. That is, you're optimizing, which I believe you can, unless someone is extremely bad or one is so good that it's already the old story. So I'm a little confused about the predictive power of doing this, because the same applies for the response. Because only if you optimize the response.
Yes, but so let's say I was able to optimize, given for a number of observables. Okay.
Yes.
If I then look at the force response, and if I'm able to get the right force response, even I am working on marginal densities. Okay, so by optimizing on for a subset of observables, I can just not maybe or mess up the other observables. But if I do get the right force response for these observables, I'm still happy.
Yeah, but then if you have other observable, you have to change everything.
Yes, but that's always the problem. Isn't it?
Well, depends.
Right? I mean, it's actually I do work with a number of people from sort of on the atmospheric side running GCNs.
I believe that.
And for example, so if you look at temperature,
Yes.
if you tune the temperature on the attractor, and if you can get the right predictions for the temperature
Yeah.
later on, it doesn't say, since I am working on marginal densities, I'm blind to anything else that happens outside. If the other observables if the interactions are strong enough to mess up my response, then I will see it.
Yeah.
Right?
But,
If I don't, then I won't.
Seems a little overfit, but maybe it's my fit.
You had a question? No. So, I'm not sure to understand. Do you assume that you are able to compare with the truth or with something else? Or with the truth?
But I assume that I am able to compare not with the truth, because this pi L is this least biased density already. Okay? So that's not really true. So this is the sort of least biased approximation of the truth. So I'm assuming I can get the first estimates on the first couple of moments of the truth, and then construct sort of the exponential type density with these L moment constraints. So it is related to truth, but it's not the full truth. I don't actually need the full truth. By the way, this is just the sufficient conditions. It's a pretty strong, it's not a necessary condition, it's sufficient for improving the predictions. Because I used the convexity property here. So it's sufficient, it's not necessary. There's someone else.
Okay, I now leave the question open to everybody of you. If we continue the discussion, it will shortcut our tea break. If you can postpone your question until the tea break, you can discuss it over a tea. Otherwise, I think we have to continue. So thank you very much again.